Hello everyone, my name is Dimitrios Tsakoumis and I will present you an overview of my PhD research within the MODAPTO project. First, some words about me. I'm about 1 year into my PhD and I work on applying alongside with other optimization methods machine learning in order to tackle some complex manufacturing problems. More specifically, I started with two applied industrial problems, which are the two pilots for the MODAPTO project, and I work mostly based on modeling and optimization of those problems right now. And next, I'm about to extend it to other data-driven methods, especially neural combinatorial optimization, which is the intersection of machine learning and combinatorial optimization, which means using machine learning methods in order to tackle complex combinatorial optimization problems. Oh, let's dive into the first pilot of the project about the case description, where we have the manufacturer that develops robotic tools like spot welding guns or rolling hemming. And the process includes selecting appropriate robots and tools, designing production cells, and simulating feasibility, and finally programming and commissioning the system. Here, digital twins play a crucial role in enabling virtual commissioning and validating the automation logic before the physical deployment. And here is the visualization of the process. And here is where we stand right here at the part about the optimization of the robotic movements. Our approach for this focus on trajectory optimization, but goes beyond the traditional trajectory optimization methods, since instead we focus solely on the path that the robot follows. By leveraging digital twins, we model the full range of possible states that the robot can operate, because we got a production cell that operates in cycles, and each cycle is made up of specific robot movements, and for every movement we can generate a set of operational scenarios that we got the global position, and via inverse kinematics we can get its axis positions for this. So for the 6 axis here, because we have a 6 degrees of freedom robot, and via cubic spline interpolation we can get the 6 axis, also their velocity, acceleration, and jerk. And we also have to specify about the configuration by grasping the status and turn that is specified at the robot code, so as to have an unambiguous robot grasping of the object, because it could do different ways, like it has the elbow up or the elbow down. And with those control attributes, we got the outcomes, which is the time required for the movement, the energy consumed, and the carbon emissions. Now, here is the optimization process, where at the input we have the current robot program code, which we analyze in order to have the current plan of the specific points that the robot goes with, the specific velocity, etc., etc. In general, the movements for the tasks. Then for each movement, we create discrete possible operational scenarios, so as to calculate the time for each scenario and to be able to query the FMU with the 6 axis for velocity, acceleration, etc. that we saw before, in order to obtain from the FMU the energy required and the carbon emissions. But because this problem, in order to be solved, is really computationally expensive, we apply Pareto filtering in order to filter out some dominated scenarios and to include only the non-dominated at the optimization model. Then we can solve the optimization instance only with the non-dominated scenarios in order to create the optimized robot program that will now be the output, but now it will contain, let's say, the optimized velocities for movements to be done. Here is the mathematical modeling of the problem, which is a simple knapsack variant, and it can be extendable also to contain other constraints about, let's say, carbon emissions, or to be contained in the objective functions. And of course, it is extendable to other variants of the problem of, like, let's say we have multiple robots, or even adding time windows per actions, so as to avoid the interlocking. And here are some information about the Pareto filtering that I talked about earlier, which is a discretization process of nonlinear outcomes. Because, as we said, in order to do this optimization and solve all these instances, it is really computationally expensive. So we filter out some of the operational scenarios, and we only contain only the non-dominated, so as to solve the optimization instance. But what is the domination that we're talking about here? An operational scenario is Pareto optimal if it is non-dominated but any other scenario, and the operational scenario have to be at least as good as another one in all characteristics, and strictly better in at least one. A very quick numerical example here would be that we have one scenario where we have the time, let's say, 10 units, and the energy is 15 units, and another scenario that the time is again 10 units, but the energy is 14 units. Since at the same time we got less energy consumed at the second scenario, of course, the first will be dominated and get completely discarded. And only the non-dominated will be at our model to solve the optimization instance. And here are some computational experiments in order to showcase this, where we have two methods, one with Pareto filtering and one integer program without Pareto filtering. This was with lab energy data. And we can clearly see how the model quickly becomes intractable beyond a million scenarios, where without filtering it can't be even calculated, while with Pareto filtering, we can drastically reduce the space while preserving optimality, especially beyond a million scenarios where we see the intractability of this issue. And here we got the other problem at the pilot 3, where here we have a kitting robot system, KRS, where there is it is a picking robot that has to fill the kit holders from the one side with the components from the other sides at the containers, which are on a gravity rack, and it has to take the components from the one side so as to fill the other side. And the objective, of course, is to design a picking route so as the KRS, which is the kitting robot system again, to minimize the time of these operations. And this problem naturally maps to the traveling salesman problem, since we again have the picking place in position, let's say, being the nodes, like the cities at the traveling salesman problem. And we have for our agent to be one time at each city here at its node, at this problem, which could be a picking or replacing position, and then get back at the first position where it started. But since at our problem there is an alternation between the picking position and the placing positions, it comes down to a specific variant of the traveling salesman problem, which is the bipartite TSP, because there is an alternation going on between two disjoint sets, one being the gravity rack and the other being the kit holder. And of course, the optimization objective is to minimize the total time required for the robot to transfer the components from the gravity rack to the kit holder. A few more words about the time calculations here. First, we got the picking time, where it contains the robot to get to a specific safe position and to be ready for picking. And then we had also the time in order to actually pick the object. And then it goes the same about placing the object, the component, so as to go to a placing safe position, and then to place the object at the other disjoint set. And as far as solution is concerned, we got 4 here with nearest neighbor being just a greedy heuristic to pick the closest unvisited node. An improvement of that as a two-opt heuristic, where it improves the nearest neighbor by swapping edges, and an exact solution by integer programming with subtour elimination, and also a reinforcement laying approach, which to the best of our knowledge is the first reinforcement laying approach in this specific variant of the TSP, the bipartite variant, with a Q learning, which learns optimal tour by updating a Q value table by using the Bellman equations, and with the rewards that the guy learns over the episodes. There is a final tour that it gets we get as an output that follows the highest Q value that we got. But here at the computational experiments, the Q learning, in order to have an optimality gap that is close to nearest neighbor, it gets with very much complexity. It gets, the time here is really huge. So there is a problem with this issue of the Q learning here that we explored. And that's why for this work, about the future work, I'm about to utilize graph neural networks in order to extend this approach and have better results. If I could describe GNNs, or graph neural networks, as short as possible, I would say that it is two things: message passing and aggregation. Because we have a neighborhood, let's say here the graph and the nodes, and some vector representations. This vector representation of the nodes could contain whatever information about our problem. And there is some message passing going on between them. The GNNs, just like the classical neural networks, contain layers. And the GNNs of the layers are the k-hop neighborhood where the message passing, we get the message passing, where the k, let's say the k is 1, which means we have one layer, that there is the exchange of the messages at only the immediate neighbors. If we got two layers, where the k-hop neighborhood for k equals 2, we also take into account the neighbors of the neighbors, etc. Just like the example right here, where you can see that the node 1, after one message passing layer, it contains some yellow and some orange because it is their immediate neighbors. While the node 4, it doesn't contain, let's say, any yellow because it isn't our in the one hop neighborhood, and we have to go to the two hop neighborhood, which means to stack another layer in order to have some information also from the node 3, which is the yellow node. So in order to do this, which is, as I said at the beginning, is a neural combinatorial optimization approach, because it utilizes machine learning for a combinatorial optimization problem. This is because GNNs are really expressive for this, as we saw in this graph, and combinatorial optimization tasks have an underlying graph structure, and GNNs would be capable of understanding to this structure so as to assist combinatorial solvers or to be trained end-to-end by supervised learning, let's say if we have the ground truth labels, or through minimizing a cost function, let's say via reinforcement learning or deep reinforcement learning. And more specifically about the TSP, we could use the embedding that we take after we apply the GNN. In order to decode the solution, we could do an autoregressive way where we predict the immediate node, the TSP tour, based on the current node that we are right now at the tour, or the non-autoregressive where we immediately output the sequence based on the edges with the highest probability given. In general, I lean into the non-autoregressive approach because it is highly parallelized and it can lead to faster evaluation here. So here we see how the GNNs could be a right fit for combinatorial optimization problems because of the underlying graph structure that they can grasp. There is also really have literature upon this, especially at the last 2 or 3 years, and this is what I'm about to do at the future work. And here are some papers about the work we have done right now, some publications at 3 publications at some conferences with proceedings that we are about to present this summer. And that's all for me. Thank you for your time.